During this presentation, we will be discussing how we can build a mathematical model in order to describe how the concentration varies as we vary depth and time. First of all, it is important to know what transport phenomena is. This is an area of knowledge that studies how mass moves around in a system based on a concentration gradient, or in other words, it means that mass will move from a high concentration zone to a low concentration zone. If you don't really think that this happens in real life, just think of how a membrane transports things in and out of it. In order to fully understand how transport phenomena works, we will be solving this specific problem. If you want to read it carefully, please pause it right now. We are told that we have a water and oxygen system within a tank. This tank is completely closed, meaning that it is not interacting with the atmosphere. As important pieces of information, we are giving the initial concentration of oxygen at a constant temperature and pressure. We are also giving the diffusivity constant between these two substances. And lastly, we are given the constant for Henry's law, which will be useful for calculations that will be shown further in this video. All this information is making me a bit dizzy, so let's put it into a diagram. Here we have a visual representation of our system, and as we can see, there will be two phases, a gas and a liquid. Because we are studying transport phenomena, we know that oxygen will move from a high concentration zone to a low concentration zone, and this low concentration zone is the water in our system. And because we have constant temperatures and pressure, we can say that the diffusivity is constant, meaning that oxygen will diffuse constantly along the depth of the tank. If you didn't pause the video when I told you to do so, then you don't know what the problem is asking us to do, so let's recall it. We're being asked to determine how much time it will take for oxygen to diffuse into the water at a depth of 0.3 centimeters, knowing that at that specific point we have a concentration of 20 grams per cubic meter. And in order to do so, we need to have a mathematical function that describes us the concentration of oxygen as a function of time and depth. We are extremely lucky because someone already invented the equation that describes the movement of mass within a system. And this is given by this general equation shown in this slide. And it can be simplified to make our lives easier and also for it to fit our system. And to do so, we need to know the following. There is movement of mass in a single direction because oxygen is moving downwards only. Then there is no convective transport because there is not a fan or something that moves around our fluids, so we can eliminate a great part of our equation. Then there is no chemical reaction because there is no mention of it in the problem. And lastly, we know that the problem is not in a steady state because it changes over time. We can now take this much simpler equation that describes how concentration changes over time and depth and put it into Wolfram. But if we do so, we will obtain a solution that is not fully describing our system. So we still need some pieces of information. The first piece of information that is missing is that at our interface, we have a saturation concentration that can be found with Henry's constant as mentioned way before. Then we know that when time is 0, there is an initial concentration of oxygen given by the problem. And lastly, because we don't know the total volume of the tank, we can work with it as if it was infinite, although it's really not. After all this time, we have arrived to the solution, which is described by this equation. And if we put values into it, we will see that as concentration increases, time also increases. Using that exact same equation and the information that we have previously stated, we can put it into an Excel sheet, and with the solver tool, we will obtain that it takes 0.27 seconds for oxygen to reach a depth of 0.3 centimeters at a concentration of 20 grams per cubic meter. Solving this problem allowed us to see that using the information that we were given in class in Fick's law, we are able to construct models that predict the concentration of a given substance in a given problem and how this concentration varies when time and depth also vary.